welcome to our lesson today. We are still on forces and what the forces can do for us. Today I want us to start by what we are calling the work energy theorem. Work energy theorem. And work energy theorem is basically the relationship. It is the relationship between work done and change in energy. Change in energy. Now, basically what we are saying is that we found out that for you to do some work, you require some energy. We also looked at the kinds of energy that we have at our disposal in our last lesson. Now, today we want to ask ourselves, how does the work done and change in energy compare? That is exactly what we are interested in when we are looking at this theorem. And the theorem states that work done is equivalent to energy change. And this time we want to restrict ourselves to kinetic energy. Now, if you do some work, we said for us to be able to claim that work has been done, scientifically, you have to apply a force to an object, and the force should result to some movement. Now, from the kinetic energy formula, it's clear for us to be able to talk about motion, then we have to put into consideration the velocity of that particular object. You have an object, you apply some force on it, the force results to some motion, and therefore we are able to talk about the velocity of that particular object. Now, if the object moves, automatically kinetic energy is going to change. Kinetic energy is going to change, and that is why we are able to talk about the change in kinetic energy whenever we talk about work having been done. Let us look at an example. Let us look at an example on the theorem. And a car of mass 1000 kgs traveling at 30 meters per second Now, a car of mass 1000 kgs traveling at 30 meters per second has its speed reduced to 10 meters per second by a braking force, and the braking force works over a distance of 75 kgs, 75 meters, sorry. Now, we are interested in A. We should determine A, initial kinetic energy. B is the final kinetic energy. And part C, we should be able to come up with the braking force. Braking force. We have our car, 100 kgs in mass, 1000 kgs in mass, traveling at an initial velocity of 30 meters per second, but the velocity is reduced to 10 by this braking force. Now, what is the initial kinetic energy? Now, from our formula, kinetic energy is given by a half mass times velocity squared, and which is to mean that the first kinetic, or the initial, was a half multiplied by 1000, and this one we multiply by the square of the first speed, and this one gives us a kinetic energy of 450,000 joules. Part B requires us to get the final, which now will be a half times mass times our velocity 2 squared, which is given by a half of 1000 multiplied by the square of the final speed, which is going to give us 50,000 joules. Now, the last part of the question requires us to get the braking force. And this is where now our theorem comes in. You say, but work is equal to change in kinetic energy. Work is actually change in kinetic energy, and that will be given by 450,000. You subtract 50,000 joules, which gives us 400,000 joules. Now, the work done by the braking force is 400,000 joules. But we are not interested in the work done by the braking force. So, how will the work done enable us to come up with the braking force? You say, but work is force times distance. Therefore, our 400,000 joules is equivalent to our braking force times our distance, which is 75 meters. We make force the subject of the formula, and force will be given by work over distance, which is equivalent to 400,000 joules, and this one you divide by 75 meters, and the breaking force is actually 5,333. It's a force, therefore we use newtons. Now, too much about that. We now look at something else, and I want us to look at sources of energy, sources of energy. Now, this energy that we are talking about has to come from somewhere, and that is why we are interested in the sources that we have, and we categorize them as either renewable sources or non-renewable sources. Now, what is the difference between the two? What is the difference between the renewable sources and the non-renewable sources? And what advantages do we have of one category over the other? Let us start with the renewable sources. Renewable sources, and these ones we say they are naturally replenished, or what we call inexhaustible. They are actually inexhaustible in nature. However much you use them, you cannot deplete them. Now, examples, we have sunlight. These are examples. We have sunlight, we have wind, we have geothermal energy, we have hydroelectricity, then we have what we call tidal energy and what we call biomass. Looking at all these sources, however much you use sunlight, you cannot deplete it. However much you tap wind energy, it cannot be exhausted. The same case applies to all the others on the list. Let us look at some of the advantages you stand to enjoy when you are using them. And the top on the list, you must appreciate that they cannot be depleted. They cannot be depleted. No, they are easy to use They are actually very cheap because they are provided by nature. They have no effect on the environment. They cannot be depleted. They are very cheap with no effect on the environment. And again, they are very easy to use. However, the initial cost of tapping them, the initial cost is too high. Is too high. Number two, some of them are not found everywhere. They are actually limited to some places. Like, for example, if you are not close to an ocean, you might not enjoy what we are calling the tidal. Therefore, they are not universal. They are not universal. Some of them, like geothermal, could emit some toxic gases. They could emit toxic gases. Now, how about non-renewable sources? Let us look at non-renewable sources. And we say they are exhaustible. Exhaustible in nature. What we mean is that over time, some of these will be depleted and you will be forced to consider an alternative. Examples of this include minerals, you cannot mine in one particular ore forever. Groundwater. Number 3 is hydrogen. Then we can have what we call fossil fuels. And when we talk about fossil fuels, we are actually talking about coal, petroleum, and natural gas. Coal, petroleum, and natural gas. Suppose we opt for these ones. What are some of the advantages that we stand to enjoy? And they will include you will appreciate that most of them are very cheap, very cheap, with no competition. Small amounts produce large amounts of energy. And again, they are easily convertible from one form to the other. Easily convertible from one form to the other. Let's also look at some of the disadvantages. And number one is that they are exhaustible. Number two is that their price depends on availability. If they are readily available, you will get them at very low prices. But in areas where they are not that easy to come by, the prices will be relatively high. And the last one is that they are toxic. They are toxic, and by toxicity we mean that they impact negatively on the environment. Now, too much about energy. Let us now look at the last item, which now is actually machines. Simple. And a machine is any device used to make work easier. Remember, our topic is on work, power, energy, and machines. Now, work will be done at a given rate depending on the energy that you have, and it will be even easier if that energy is applied on a machine. Now, why do we say that machines make work easier? What do you use them for? You will use a machine to lift large loads using little energy. Or force, for that matter. You can use a machine to enlarge the magnitude of force. You will use it to enlarge magnitude of force. You will use it to increase the rate of work. And finally, a machine can also help to change direction of force. A machine can actually lift large loads. That is why we are saying it makes work easier. And it will do that if only it increases the magnitude. Magnitude is the size of your force. Sometimes you could want to improve your rate of doing work. You will have to use a machine or probably even change direction of force. You can use the machine to do that. Now, before we look at the types of machines that we have, let's go to look at a few terms that we are going to interact with in the course of studying our machines. Therefore, let us look at a few terms that we associate with machines. And number one is what we call the effort. Symbolize it with capital E. And this is actually the force applied on a machine. Force applied on a machine. Can consider another term which we are going to call the load. Again, we write it as L, capital L. And this one is the force lifted by a machine. You apply some force on a machine which we expect is going to be increased in magnitude and output as a bigger force. And that is the force we are going to use to lift our load, if that is what we are after. We can also look at effort distance. Effort distance. Effort distance, or what we can write as E subscript D, and this is the distance from point of support to that of application of the effort. That distance from the point of support and to where now you apply your effort is what we call the effort distance. Another one is the load distance, and the load distance is actually the distance that is the distance from the point of support. Again, note that all the distances are measured from the point of support and to the line of action of the load. And this one we also write it as L subscript D. Now, let us look at work input. Work input. And work input is actually the work that you do on your machine. The effort you apply is a force. Now, we have looked at the distance, which we called the effort distance. Now, if the effort you apply on the machine is supposed to do some work on the machine, then work input is what we'll be talking about, and this is the work done. Work done on the machine. By the effort, and is given by work input is given by effort you multiply by effort distance. Effort multiplied by effort distance is what is going to give you work input. Now, remember, we want to make work easier. Therefore, the work we do on our machine is supposed to give us some result, and that is what we call the work output. Work output is actually the work done. This time by the machine. On the load. Work output is the work done by the machine on the load, and is going to be given by load, and this we multiply by the load distance. Load you multiply by the load distance. Seven is what we call the fulcrum, or the pivot. And this is the point of support. Point of support of the machine. you can either write it as P or even F. Now, next we have what we call mechanical advantage. Or MA. And mechanical advantage is actually the ratio of load to effort. Mechanical advantage is the ratio. Remember, load and effort are both forces. Therefore, if mechanical advantage is the ratio of the two, then it means it is a ratio of two forces. Therefore, it does not have units. It does not have units. And if it is a ratio, then it is going to be given by load over effort. Now, let us look at an example. Let us look at an example on how to calculate mechanical advantage. Let us look at an example. Calculate the mechanical advantage of a machine that uses mechanical advantage of a machine that uses a force of 250 newtons to overcome a force of 600 newtons. The question requires us to get the mechanical advantage of a machine that uses a force of 250 to lift another one of 600 newtons. Now clearly you can see that the machine has actually magnified 250 that was input to 600. Therefore, there is some advantage that the machine has brought about, and that is what we are after. And say that mechanical advantage is given by load all over effort. Now, in this case, our effort is what the machine uses. The effort is 250 because that is what has been put into the machine in order to lift a load of 600 newtons. Therefore, our load is 600 newtons and our effort is 250 newtons. And again, you see the units cancel out and you are left with 2.4 as the mechanical advantage. Let us look at yet another example. And the question requires us to determine the mechanical advantage of a machine that requires a force of 650 newtons to lift a load of 1500 newtons. And again, we remember that from our formula, mechanical advantage is given by load over effort, which in our case is going to be 1500 newtons divided by 650 newtons. And this is going to give you 2.307 as the value of mechanical advantage. Now, from the previous example, we had our mechanical advantage at 2.4. Now, this time we are at 2.3, slightly lower. But we would expect a machine to help us a greater deal. Why then is it that the value of mechanical advantage does not go as high as we would expect it to be? Now, number one is that mechanical advantage is dependent on the friction between parts of the machine. Now, this explains why we need to lubricate our machine every now and then, because if there is too much friction between the parts of the machine, then automatically our mechanical advantage is impaired. And number two is that some energy is lost in lifting the movable parts. Some energy is wasted in lifting the movable parts of the machine. Therefore, friction in itself opposes motion, and therefore, if there is friction between the movable parts of the machine, now automatically this one is going to translate into a smaller value of mechanical advantage. And the same case applies to the parts of the machine. If the machine has too many movable parts, you will require some energy to lift those parts of the machine. Now, we look at another term, and the term is what we call the velocity ratio. The velocity ratio, and velocity ratio is the ratio of effort distance to load distance. Velocity ratio, again, you realize that it is a ratio of two distances. Therefore, we expect that it is not going to give us any units since it's a ratio of two distances. Therefore, in numeric form, we write it as the ratio of effort distance to load distance. For example, I will work out a question involving velocity ratio . We are told that a box of mass 75 kgs is to be lifted to the back of the lorry 1.5 meters high, and we want to find now the velocity ratio of the system. But we have said that velocity ratio is given by effort distance over load distance. Say in our case, if we are to lift it through 1.5 onto the back of a lorry 5 meters long, then it means the load is moving to 1.5 meters high, but the effort with which we are going to lift it is to move 5 meters long of a path. Therefore, our velocity ratio now becomes 5 divided by 1.5, and that should give you 3.33. Take for example, our load is here on this level. We want it to go to the back of a lorry 1.5 meters high, and we want it to follow this path, that inclination, which is 5 meters long. But in essence, the height to which we lift the load is actually 1.5. Doesn't matter what path is followed, but the end result is actually a lifting of 1.5 meters. Therefore, if you use the inclination, you will apply some force through this distance, but with an aim of taking your load, which is somewhere here, to a height 1.5. So the load will only have moved from the ground to a distance of 1.5 meters high, but through a much longer path. Now, let us look at the last term. The last term that we associate with a machine. And the last term is what we call the efficiency. The efficiency symbolized by mu, and the efficiency is actually the ratio of mechanical advantage to velocity ratio expressed as a percentage. Now we have already calculated the velocity ratio and the mechanical advantage. We therefore need to know how do they compare and what percentage of efficiency do we realize with our system of machine. And in numeric form, it's actually the ratio of mechanical advantage and velocity ratio. You express that as a percentage. You could also define it as the ratio of work output to work input, again expressed as a percentage. Expressed as a percentage. And numerically, you can write it as work output or work input. And this one, you express it as a percentage. Let us look at an example on efficiency. A simple machine, this is example, a simple machine has an energy output of 200 joules. If its efficiency is 75%, what is the work input? Again, you realize that you have been given the efficiency and the output. Now, we are after the work input, but efficiency, or we can use the symbol this time, is given by work output divided by work input, and you express it as a percentage. That's to mean 75 has been arrived at by taking our work output, dividing it by work input, and expressing it as a percentage. If we try and make work input the subject of our formula, now the equation changes to work input is equal to 200 times 100, and this we divide by 75. And the work input will be 266.6. Now, next time we meet, we will look at types of machines and probably discuss each one of them and see how they differ from each other. Thank you.